Okay, so we continue then where we left off in terms of the validity. So we extracted, can we delete this one so it doesn't confuse us because we did not accept this one. So that the last one is the one we accepted. This one, 7, yeah. So this is the one we accepted. So now what is different with reliability, we are not gonna go and throw all the items. So we're gonna use this pattern matrix to do our reliability. But now because we are measuring scale reliability, so each construct or each factor was made out of a number of items and that makes up the scale. So now we want to know how reliable is that scale. So now we go to analyze, you go to scale, go to reliability analysis, and then now we are guided by these items now as to what we're going to be checking reliability for. So I want to start with the dependent variable, which was performance. Okay, so we've got performance here, which was factor number 1, 2, 3, 4. Factor number 4. Factor number 4 scale, which is performance. So now how do we do this? So you go and we look at all the items that loaded onto performance. We had return on equity, return on investment, net profit margin, and return on assets. They all went onto the performance factor. So we're going to load those ones. So it is 2, 4 items. Let me see if I got it right. 2, 4 items. Yeah. So now we don't put all of them. We focus on one scale at a time. So we're going to go to the statistics. So we want to see the item with the scale if deleted, the inter-item correlation, and then we run that. Why we want to see this is going to give us the overall scale, the Cronbach alpha. This one is going, the scale if item deleted is going to tell us which item we must delete to improve the reliability. And this one is going to tell us how each of the items within that factor are related. Likely we want them to be 0.3 and more for that relationship to hold. And then we say, okay. So this is our first scale that we test reliability for, which was factor 4, and it was business performance. So 4 items, our Cronbach alpha is 0.922. The rule for a reliable scale is that it must be 0.7 or more. Then it's a very good scale. In management studies, some do take 0.6. 0.6, they say it's okay. Some does even take 0.5. Because this is all about the risk. So management studies, if you were wrong about the fact that your scale is reliable at 0.5 and is not reliable, the risk is low. Because basically no one is going to die by you using that scale. But if you start getting to analyzing things that has got higher risk, either somebody's going to die or it's something that is risky, then the cutoff becomes very strict. But with management studies, entrepreneurship study, digital coaching, the risk is low, so you can afford to go lower. So, but here we've got an excellent one with 4 items. We've got 0.922 as our Cronbach is higher than 0.7, so we are happy. Let's see if there's a way we can improve this. Okay, the inter-item correlation, all of them are higher than 0.3, so we are happy. And then our main scale is 0.922. Let's see what are any suggestions. So here, whatever item we remove is going to reduce the reliability. So we are not going to remove any. because we are fine with what we have is higher than all of this. So this column that says Cronbach alpha, if item deleted, it means if you delete that item, the Cronbach alpha will become, overall Cronbach alpha will become 0.891 or 0.884902, depending which one we delete. But because we already have 0.922, we are fine. So we don't want to delete anything. So that was item, that was scale 1.
Dr. J, the correlation shows.
I'm listening.
Dr. J, on correlation table.
Yes.
If it shows less than 0.3, what are we to do? Are we
so you can,
that?
Yeah, you can let that item go if you can afford to, because it all depends on whether you've got enough items as well. Remember, it goes back to that managing what you have, because you don't want to go lower than 3 items. So if we had an item here that correlates maybe, let's say 0.1 to the other items, we can let that item go. Because we can afford to, because we've got 4 items. But if it does not have, we've got already 3, we keep it, and then as long as our overall reliability is good, we rely on that. So because it's multiple things that we're making decisions on, so I look and say, okay, my inter item 0.3, I get that item go. How is it going to change the overall correlation? Is it going to improve it? And most likely you'll find that that item that's got a lower inter-item correlation there will be the one that is suggested to be removed here. And then if you remove it, does it improve then the overall item there? If it makes it worse, then leave it. If it improves it, then you can let it go. If you already at the minimum 3, then you keep it. And then you just have to, with stats, all you have to do is you have to support why you are keeping it. So you can say, okay, as much as it was lower than 0.3, but because the overall Cronbach was higher, was even excellent, was at 0.9, and when deleting it is going to reduce the overall alpha. Therefore, in this study, we decided then to keep it. So you just have to support whatever decision that you make. Okay, so that is factor 1, the scale for our dependent variables. So we have to repeat this process for all the different variables that you have. But I'm just going to do one more because it's exactly just the repetition. I'm not going to do all of them. So let's say we decide to take, let's take the first one, factor 1. Let's write the scale for factor 1. So let's say we call our factor 1, let's call it self-efficacy. And then now we must put the items that belongs to factor 1. Take those ones out. So factor 1 had hardness 2223. It has self-efficacy 20, 21, 22, 23. It had zest 21. It had bravery. Have I put bravery already? No. It had bravery 22, 23. And then, so how many items do I have? 2, 4, 6, 8. 8. So I've got all of them in. And then, so unless you reset this, it will still be selected. So I just continue. And then now my scale for self-efficacy, which was factor 1, is 0.831 with 8 items. Let's see whether there's any suggestions. You've got some items that are lower than 0.3. So this is 0.24. 0.282, so you've got some lower than 0.3. Let's see what this is suggesting. Our overall is 0.831, 24. So none of them will improve the scale. In fact, it's going to lower them. So I'll make the decision to leave even these ones that are 0.2. If you round it off, it's 0.2. 4.3 to 8 can be 0.3. So I'm fine to keep them. So I'll keep those ones because otherwise it's going to reduce the reliability, decrease the reliability. So 0.831, I'm good. 8 items, more than enough. And if you decide, oh, I've got enough items, 8 of them, I can take it off, it's up to you. It's really no fixed way to say, choose, go this way or that way. It's your discretion, but you just have to support why you made the decision that you have made. So that's, yeah. So you're going to repeat this process 8 times because then you do a scale for each of them. And then once we are done with all now, they're repeating all of them, all the scales, then now you've got reliable and valid, you've got valid constructs and reliable scales, then the next step. So what did we say our next step is? So our next step now is to get the composite scores, because now we can reduce then the dimensions of our data into a smaller data set with fewer items, which we'll use as our variables. So let's use the ones that we just did now. I'll just do one to show you, but you repeat the process for all the 11 vectors. So let's use the one that's got fewer items just to make it easy. So now to create the composite score, you go to transform, compute variable, and then you need to go to the stats side here on the list, statistical. Then you can choose the method you want to choose to combine your items. So I choose mean. And then you have to say here what you're going to call the factor. So it was business performance. I'll use it caps so that it's different from all the other items. Then I know this one is already the final variable. So it's composite score for business performance. It had 4 items. So we're going to add all the items into that calculation. So we had the return on investment. We had the return on equity. Then you just keep putting commas and double click. We have then the net profit margin, and then the last one was the return on assets. If you say okay, then it's going to give you the composite score. So if you want to check if what you were doing was recorded, took place, then it will be recorded on your output file. So it tells you here, you've taken a mean of return on investment, return on equity, net profit margin, and return on asset. And it's executed. So if you now go back to your file, your data view file, you go to the end. You will see you've got a new variable now called business performance. And then now it has taken all the 4 questions or the 4 items that loaded on that specific factor, factor 4, which was business performance. And then now it has taken an average of that. And going forward, you don't go back to the individual items anymore. From here going on, when you talk of business performance, you're going to use this as your variable because now you have created the composite score. And then what you do is that you're going to repeat this process many times of the factors. So you're going to repeat it 7 times, doing composite score for each of the different factors. So I'm not gonna do all of them, but because we've already, I'm looking at the wrong factor now. So, but because we've already done this, you know the principles and how to do it. I'm not going to do it 7 times, otherwise it's gonna waste time. So I'm going to skip this. So when you go back to our chapter 4, so now we have done our composite score. So the next part now is doing assumption testing. So we want to look at the descriptives and stuff. But because on the data set, I already did all the factors. So I'll now, I'm not gonna use this one. I'm gonna use these ones that I've already created on my earlier on before we started the class that represent the different factors. So these are already the composite scores of the different factors, but I did not label them. So, but you will get to label them obviously like we did with this one, but just for illustration purposes, I'm going to use these ones now. So if you want to maybe make life easy for yourself, you can close the output where you did your validity and reliability and kind of like label it. Your output 2 was validity and reliability. Now we're going to do regression. So we're going to close that one because we've saved it already. Okay. So now we're going to use all of them. So we're going to now do our regression. First, we want to see normality. So we're going to go back to descriptives and do our descriptive test, but now we don't want tables, we just want the stats. We want to see the mean, the median, the mode, the sum, the minimum, the maximum, the skewness. This is what's going to tell us about the normality. And which items we want to run this for. We want to run now for what we have created composite scores for, which is now what we changed the lingo. Now it's not factors anymore. We call them now variables. So this is what was in our factor analysis. And the composite scores, and it was reliable, so the composite scores. And then we run that. Okay, I didn't want the bar chart, just wanted that. Okay, so now when you look at this table, so we had 282, our sample size. We had no missing values on the key variables as much as we might have had on the demographics, but we didn't have on the key variables. We are interested in the skewness and the kurtosis. The rule says that for skewness to be treated as normally distributed, it must be close. I think some look at 1, some look at 3, that depending who you're going to reference. Some say for the kurtosis 7, some say 10. So let's work on 3 for skewness and 7 for kurtosis. So if you look at this, all our variables, none of them is 3 or -3. And then our kurtosis, none of them is 7 or -7. So we can treat this data as normally distributed. If we had maybe, let's say for factor 1, which will be your variable, you will have labeled it. If you had here maybe 8, for an example, then you know you don't have normality. The data is not, that variable is not normally distributed. So you have to do data transformation. There's different rules that guides you how to do your data transformation. You can either use the log, you can use a lean, you can use exponents, you can use inverse. There's different things. So you just need to read and understand which method is best for which. They recommend either based on whether you are skewed to the left or you are skewed to the right. So that is something you can read. It's in one of my slides. If you want it, I can share. But those are the rules you follow. So here we've got normal data close enough to normal distribution, as much as most of the variables are negatively skewed, but they are close enough to, because they are not above the negative plus minus 3. And then the kurtosis, as much as you've got them at 3, one of them is at 3, but you're not at 7, which is the cutoff, so it's fine. So we're gonna treat these as normally distributed data. So now we wanna test linearity. Let's see how linearly correlated they are. Let the linearity. So what you do on linearity, you go to correlate, so you go to analyze. So you'll use analyze a lot. Let me just give you a high level. So you will use transform if you are computing something. If you want to calculate something, adding, subtracting, whatever, you use transform, and then you compute variable. There's different one if you want to recode and those kind of things. This is where you're going to be working a lot on transform. But all your analysis, most you will go to these analyze tabs, and you can play around here, then you can see the different types of analysis that you can do. So we want to see linearity, so we're going to do correlate by variate. So we want to see linearity between our variables, which we created from the vectors. Okay, because we've got normal data, normally distributed data, so we're gonna use Pearson. If your data is not normally distributed, you need to use Spearman, but we are happy with the normal distribution, so we're going to use that. There's nothing you need to change here because we've already addressed missing value issues. Bootstrap, so you can use Bootstrap sometimes if you've got a small sample size and then you want to just double check your results with a bigger sample. So what Bootstrap does, it mimics your data distribution or data characteristics into a sample of 1,000 and then runs parallel results on that, and then you can be able to compare, but it takes time to run. I'm not gonna do that, and I trust that you will have enough data set to run that. So then this becomes your correlation. Obviously, you don't take it as raw as it is and go present it in your report. You need to clean it up, because if you look at this, you will see that you look at this technical side, the upper part is just a mirror of the bottom part. It gives you exactly the same information. So the first line, Pearson correlation, it gives you the correlation between the two items. So factor 1 and factor 2, they are negatively correlated, and at 0.464. If you were to change this into a percentage for your own maybe ease of understanding, it is about 46%, so that is the correlation. You've got some guidelines in terms of what is a good correlation, what is a weak, what is a strong, what is a medium correlation. Most studies say below 0.3 is weak, 0.3 to 0.5 is medium, 0.5 and above is a strong correlation. So you've got 0.46 here, negatively correlated between variable 1 and variable 2. So that is medium. That is lower than medium, so that one is weak. 0.5, medium to large. So that's how you interpret this one is weak. 0.16, that's how you interpret the first line, which is your Pearson correlation coefficient. The second line tells you about the significance of that relationship, which is basically a repetition of this asterisk here. So if you look at the bottom of the table, you've got these two asterisks. It tells you that it is denoting a significant relationship at 0.01 level, and one asterisk at 0.05 significance level. So how you interpret this, so 0, it is less than 0.05, less than 0.01 as well. So you've got the two asterisks, so you'll interpret it according to the 0.01. So what you will say is factor 1 negatively related to factor 2 at 0.464, and that relationship is significant because the P is less than 0.01. So that's how you interpret that. So that is your correlation. So from what we're getting, we've got significant relationships higher than 0.3 mostly. So we've got linearity. So assumption 1, we've got normality. Assumption 2, we've got linearity. So we are fine to proceed with our linear regression. Okay, so some of the things.
Dr. Jay,
yes.
Can you please go back to that last table?
The correlation.
And you'll see you're on factor 7 and factor 5. There's a significance of 0.213 and a Pearson correlation of negative 0.74. How do we interpret that?
Yeah, that is a weak, weak insignificant relationship.
Okay.
But remember also what is important in this table. Remember, you're going to be looking at dependent variable against independent variables. The linearity needs to be between your dependent with your independent variables. It doesn't have to be with your independent to independent. It's just that I didn't name them to see which is which, but you will find that your dependent and your independents are fine. And then you'll find maybe one independent is not significant. You can still keep it and run the test, and then you will interpret it when you run your hypothesis to say why that one didn't work. So if I had them labeled, then we will be able to tell whether all the independent variables are significantly related to your independent. I mean, all the independent variables are significantly related to your dependent variables. So it's just that I did not label them just for illustration purposes, but that's what you pay attention to, is the relationship between your dependent variable versus your independent variables, not the relationship between the independent variables themselves. Between the independent variables themselves, what you're interested in is multicollinearity. You don't want them to correlate between themselves higher than 0.9 or 0.9 and more. So those are the things that you pay attention to. So using this table, you can somewhere also decide in terms of the multicollinearity. So there's no multicollinearity here. Nothing is 0.9. So you are fine in terms of that. Okay. So the other thing we need to test now is so we've looked at, oh, we should have started with the outliers. We need to check the outliers. I forgot that, because if we've got outliers, we're going to change the data, so it's going to affect the other things that comes after. And also it's going to adjust our normality to be closer to the normal distribution. So let's see the outliers. So I normally use the box plot, easy to interpret, but you can also run it within the regression. So we want the outliers of our vectors. So I run all of them at the same time. It's quicker than running one box plot at a time. So if you look at this, I think this data set, I already cleaned it. But if you've got outliers, what you will have, you'll have an asterisk. If you've got an asterisk, then it shows you that you've got an outlier. But if you just have the circles, it's a bit out the normal range, but it's not an outlier. So you can still treat it as not an outlier and continue with the data set. So if you look at all the different variables, none of them has got an outlier, so we are fine. This you can put in your report. This you can put in the report after you clean it up. Normally it works best if you clean it up and then you combine the correlation with the mean and the standard deviations from here, and then make it one table. You can read articles and see how they present it nicely. And then we are happy with that. Let me see if I can find the file where I ran the part that still had outliers, just to show you how it looks like. Okay, yeah, so this one is where I had outliers, which I've already cleaned on the one that we just did now. So you see that 200 there. So what that 200 means, it tells you that observation number 200 is an outlier. Observation number 188 for factor 2 is an outlier. So that's how you read this. Observation 232 for factor 6 is an outlier. Observation 8 for factor 7 is an outlier. So you can use, so what I used to clean it up, I used what is called Windsorizing. So what you do is that if you look at this, just show you what I did. I think I deleted them. Oh, here. So what you can do, you can look at this table and see what is the highest values that you have. So when it tells you observation 29 is a outlier, what Windsorizing suggests is that you need to go to the next highest observation, or look at what is that value, and then you substitute whatever is deemed an outlier with the next highest, or the second highest number of value, and you substitute it with that. So like in this case, if 29, 49, 95, and 257 are flagged as outliers, we will substitute them by 6.83. So that's how you deal with the outliers. If you've got more than enough data set you can afford to delete, it's up to you, you can delete, but mostly you can use Windsorizing and take this. So if your higher point was 7, your next highest point before 7, then you substitute the higher one until then you get to a point when then you've addressed all the outliers. Does that make sense? I'm sure you're tired now, you're not even hearing me.
Makes sense.
So with you, it's just intense.
Okay, the nice thing is that we're recording. So how you get this table that I was showing you now that you can use to check your extreme values, you run it under Analyze. And then you go to the descriptives, you go to explore, and then you can put your whatever that you want to analyze there, whatever the variables are, and then you can be able, you click outliers, and then it will give you some of the numbers there that I was showing you now, and then you can use that to kind of like check as to which one is the highest and those kind of things. So it gives you this, you can use this table then to see the highest, and then keep on reducing it until you get to an acceptable range. Okay, so that was outliers, linearity, normal we've done, collinearity we've checked. So the errors and the observation independent, what really that it means is that each response must come from an independent person. So one person can't answer multiple times. So that's what independent observation really means. It's independent. The sample is like Jabu answers independently, Lashan answered independently, Katie answers independently. So there's no link between that. And then the normality of errors, we'll test that when we run the hypothesis testing. Is easier to get the results there. So let's do that at the same time. So let me just close that to make it quicker. So yeah, so we've ran our outliers, happy. So outliers we're not violating, linearity we're not violating, and normality we're not violating. So we can run our regression. So there's, yeah, you were asking about different regressions, Lashan. Here's a lot of different regressions, but each of them you need to you need to read and understand their rules. Like linearity, all the assumptions we've looked at and all that, each of them have their own rules in terms of how the scale you use to measure your dependent and then your independent and all that. So you will need to read and understand them. But linearity is the mostly used one. So if you go into the textbook, I think there's 3 textbooks I recommended for you guys to use. There was Discovering Statistics, and then there was the Multiple Regression something. That book will give you all the different types of regression and when you use which one. There. So, but in this case, we are using the linearity one. So when you run your regression now, so what you will need, you need to have your dependent variables. So I'll go back and use the one that I've done here. So you need to have your dependent variable in there because I can't remember the factors which. I'm just gonna use 3 of them. And then this becomes your independent variables. So in this case, your independent variables will be the different dimensions according to how you have labeled them. The different dimensions of resilience becomes your independent variables. So you go on to statistics, you want to see your confidence intervals, you want to see your Deben-Watson. So if some of the assumptions you did not do them up front, you can do them here. Like if you want to use the outliers to test them using the standard deviation, you can click here and choose that. Okay, so if you choose to run your testing same time for outliers, you click that and then you can choose outlier. Anything outside the standard deviation of 3 becomes an outlier, but we've already done that, so we don't need this. The Deben-Watson gives you the, I think it's independence of errors, if I'm not mistaken. And then R-square change, you only select it if you're doing hierarchical regression. So if you are doing a mediation or something like that, then you want to run your regression in steps, then you will choose R change, but we're doing it the once off, so we don't need that. Collinearity will give you the results on multicollinearity of your independent variables. We've done that already from the correlation table, but we can check it again just to see how it looks like if you're doing it here. And then the plots, you want to test the normality of your independence of your errors. So you're going to have your Z residual represents your Y, so that is residuals for your dependent. You want to have your Z predict residuals for your independence. There you want to see the histogram to show you how normal they are, and the normality plot to show you that. So by default, it gives you 95%. Your F value will test at 95%. So we're fine. We don't worry about this one because we've already addressed the missing value issues. And then we run that. So then this is your regression results. It gives you again your correlation table. So it's just represented differently from when you ran the bivariate. So this one gives you the coefficients first, and then it gives you the significance, and then it tells you the sample size. The one we ran earlier, the table combined everything for each variable there. So these are the things that now you need to analyze. Remember, our hypothesis said resilience dimension positively influences business performance. So we've got our dependent variable here as business performance, and then we've got 3 dimensions here of resilience that we are looking at. So what you analyze from this table, you first look at the R square. So what the R squared tells you is the variance explained in this model by the 3 independent variables on the change that is happening on performance. So if you were to change this into percentage, what it says really is that about 2% of what is happening onto performance is explained by these 3 dimensions of resilience. And then we want to go and understand further, is this 2% explained here significant? Then you come to the ANOVA table, you look at the last part, which is your significance. So this is comparing your p-value to your 0.05. You've got 0.95, which is greater than your p-value of 0.05. Therefore, this model is insignificant. So whatever that the 3 dimensions of resilience is explaining on the changes in performance, it is not a significant explanation, or the predictive capacity there is not significant, so it's nothing to tell home. And then if this was less than 0.05, then we will say our model is significant. The 3 dimensions of resilience significantly explain in the model what is happening on performance. But in this case, it is greater than 0.05, so it's not significant. It's not significantly explaining it. So resilience does not have a significant predictive capacity, so we can't use it to really explain the performance of the business or whatever that is happening on business performance. The collinearity, if you were to interpret the multicollinearity here, you can say that then I think the cutoff is 10 for VIF. If this was greater than 10, then you'll have multicollinearity issues, but it's less than 10, you are fine. The tolerance level, I think, is what is it? I forgot now. I'll check it for you, but it's in the notes. But it's less than that. I think it's 2. So you don't have multicollinearity issues. So that is if you are interpreting multicollinearity at this level. But we did it with the correlation. And then in terms of the coefficients, now you want to analyze each resilience dimension on its own. As much as the overall model of the 3 of them is not significant, we want to see each of them, how it is doing in predicting business performance. So dimension 1 is about negative 0.002. So dimension 1 negatively influences business performance, but it's still not a significant one. So this significance is greater than 0.05, so it's not significant. So we can say then if we had hypothesis dimension 1 positively influencing business performance, number 1, the result is not supporting the hypothesis because it is negative, it's not positively influencing it. So it does not support the hypothesis. Number 2, it is not significant. So what we hypothesize for dimension 2 to be influencing a business performance positively does not hold. So we cannot accept that hypothesis. So we contradicting what literature suggested or what we hypothesize. Dimension 3 is about 0.214. So for every unit change in performance, in dimension 3, performance will change by 0.214 units, but it's still not significant. So there's nothing really to take home. As much as the positive influence is supported, it's positive, but it's not significant. The same with dimension 4, the same story. As much as it supports the positive influence, but it is not significant. They're all greater than 0.05. So if you were to use the beta, the standard beta, and convert it into percentages, if you change this one, it's like 0.01% negatively influences performance. This one is about 10% influencing performance, but not significant. And this one is about 6% influence on performance, but still not significant. So that is now looking at each of the different dimensions. So basically the overall story is that you cannot use an entrepreneur's resilience or level of resilience to predict how his business is going to perform, because there is no significant influence of the different dimensions of resilience onto performance. And at the same time, one of the dimensions is negative, so it really influences it the opposite direction. So if you've got high of that, then your business performance is going to go low in terms of that type of resilience. So that's basically the story of your regression analysis. This was you testing the normality of the residuals. The bell shape curve looks close enough to normality, so we are happy. And also the QQ plot, so your dependent variable, also it looks close enough to the straight line, so we are happy that then it's normally distributed. Linearity, you can use the scatter plot to look at that. And also for homogeneous, which I did not add on the list of assumptions we need to check, it is homogeneous variance. What homogeneous variance means is that the variability in between or within your different observations, it is kind of like uniform, and then you don't want to violate that. And normally when you get here and this forms some kind of a pattern, then you know you don't have homogeneous variance, and then you're violating that assumption. But looking at this, it looks fine. It's not much of a difference. Most of the as much as here you get a bit of a cluttered kind of variation in between, but overall it looks fine. We can live with that. It's not that much clearing. And that is the end of your really chapter 4. And then the next thing is you put this table in your report, you put this table in your report, you put this table onto your report, you put this one under your assumption, this graph under your assumption, you put this one under your assumptions, this one under your assumptions, and then you interpret your results. And that is your chapter 4. Any questions? Are you still awake?
Yes, Dr. J, I just wanted to find out if let's say your results do not support your hypothesis, how are you supposed to present the results? Do you have to change your data, or is it fine as is if it's not supported by the results?
Remember, your objective of the study was to find out in your context whether what literature has suggested or what other people have found in their own research will be the same or different in your case. So whether it is supported or is not supported, that is the finding. That's what it is in your case. For an example, the example we used of resilient entrepreneurs and how that influences their business. Somebody else might have done the study in the US and find that entrepreneurs who've got high level of resilience have businesses that perform better. But when we do it now here in South Africa, it says no. The South African context works different, as they can be, they can have as high as possible of the different dimensions of resilience. It does not change, does not influence their business performance significantly. And that is the finding. And that's what you need to report. But then when you get to chapter 5, now what you do is now you start talking to your findings, comparing to what chapter 2 has said, and then now you start reasoning it to say, literature in chapter 2, author blah, 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 said that resilient positively influences business performance. But in chapter 4, I found that resilient does not influence performance. Therefore, the reason my results is different from author 2 is because his context was blah, 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 or he looked at these, or he mediated certain things which I did not mediate, or you find other studies that agree with you and then others don't agree with you, and then you make your argument using those things. So chapter 4, you just present what you have found, you analyze it. Chapter 5, you compare what you have found versus what literature suggested is the case, and then you compare different authors to see who found this, what was their context, what was different, what is it that you did different, that they did maybe different from you, and then you make an argument, and then you make your conclusions then from there.
I get it. Thank you, Dr. J.
Okay. I know I said we're gonna finish at 12. I'm sorry, I didn't think it would go that long. Any other questions?
Thanks, Dr. J. With regard to chapter 4, would you want it the whole paper together, or should, once we've done chapter 4, send that to you as the supervisor?
What works for me is that you keep the chapters together. Don't write it in separate documents, because then you just create extra work for yourself. But when you send to me, you might have chapter 4 finished, you still need to work on chapter 5 or whatever, or you've got a draft of chapter 5. When you send to me, just tell me to say, for now, can you just check chapter 4 for me? I still need to do this and this on the other chapters. Then I know that's what I check. It's better to finish the chapter 4 and send to me before you get to 5, because then if there are flawed things in chapter 4, when you change them, you will need to change chapter 5 as well. And you don't want to do the same chapter twice.
Noted. Thanks, Dr. J.
Okay. Siviwe, in terms of presenting your hypothesis and your results, does it make sense now?
Yeah, it does. This was very valuable, Dr. J. It makes sense now, yeah.
Okay. And we are clear with the structure of chapter 4.
Yes. I know exactly now how I'm going to put it together.
Okay.
Thank you. Okay.
I'm trying to look at what you guys said earlier as to whether I've covered all of it. If I left anything that you raised, let me know. But I think I've covered all of it.
Dr. J, you need to add this as a module on the MMBAC.
The thing is, most MMBACs do quals. So you wouldn't want to get the whole class to sit for quants to go do quals. So, and in the past, before I started, nobody did quants in MMBAC. So I'm the one who just started forcing it in because we've got enough quals studies on coaching. So we need quants now. So in MME and VC, Prof. Boris is like, he does not like quals at all. So he forces everybody to do quants. Okay.